Atmospheric corrosion damage mechanisms part of uniform or localized loss of thickness. Description of atmospheric corrosion based on API 571. A form of corrosion that occurs from moisture associated with atmospheric conditions. Marine environments and moist polluted industrial environments with airborne contaminants are most severe. Dry rural environments cause very little corrosion. Atmospheric corrosion is the gradual deterioration and destruction of materials, primarily metals, due to their reaction with the surrounding atmosphere. This type of corrosion occurs when materials are exposed to air and moisture, leading to electrochemical reactions on their surfaces. Key factors contributing to atmospheric corrosion. Number 1 is moisture. The presence of water in the form of fog, dew, precipitation, or high relative humidity is crucial for atmospheric corrosion to occur. In completely dry conditions, corrosion is minimal. Number 2 is oxygen. Oxygen in the atmosphere reacts with metals, forming oxides. For example, iron reacts with oxygen to form iron oxide, commonly known as rust. Number 3 is pollutants. Industrial pollutants like sulfur dioxide and chlorine can accelerate corrosion by forming acidic compounds when combined with moisture. Number 4 is salts. Salts, especially those containing chloride ions, can form electrolytes that enhance the electrochemical reactions leading to corrosion. Number 5 is temperature. Higher temperatures can increase the rate of corrosion by making electrolytes more reactive. Effects of atmospheric corrosion. Number 1 is structural weakness. Corrosion can significantly reduce the mechanical strength of metals, leading to structural failures. Number 2 is aesthetic damage. Corrosion often results in unsightly rust and discoloration on surfaces. Number 3 is economic impact. The need for maintenance, repair, and replacement of corroded materials can be costly. Examples of atmospheric corrosion affected areas. Number 1 is outdoor structures. Bridges, buildings, and monuments are commonly affected by atmospheric corrosion. Number 2 is vehicles. Cars, ships, and airplanes can suffer from corrosion, especially in coastal or industrial areas. Number 3 is utilities. Power lines, pipelines, and other infrastructure are also vulnerable. Understanding and mitigating atmospheric corrosion is essential for maintaining the integrity and longevity of various structures and materials. Atmospheric corrosion affected materials based on API 571. Carbon steel, low alloy steels and copper alloyed aluminum. Atmospheric corrosion can affect a variety of materials, particularly metals and some nonmetals. Here are the most commonly affected materials. Number 1 is metals. Number A of metals is iron and steel. These are highly susceptible to rusting when exposed to moisture and oxygen, forming iron oxide. Number B of metals is aluminum. While it forms a protective oxide layer, it can still corrode, especially in the presence of chloride ions. Number C of metals is copper. Copper develops a green patina over time due to exposure to air and moisture, which can eventually lead to corrosion. Number D of metals is zinc. Often used as a protective coating, galvanization, zinc can corrode in acidic or salty environments. Number E of metals is nickel and nickel alloys. These materials can corrode in industrial atmospheres containing sulfur compounds. Number 2 of the most commonly affected materials is from nonmetals, includes. Number A of nonmetals is concrete. While not a metal, concrete can suffer from atmospheric corrosion, particularly when reinforced with steel rebar, which can rust and cause structural damage. Number B of nonmetals is polymers. Certain polymers can degrade when exposed to UV radiation and atmospheric pollutant. Number 3 of the most commonly affected materials is alloys, includes. Number A of alloys is stainless steel. Contains chromium, which forms a protective oxide layer, but can still corrode in harsh environments, especially those containing chlorides. Number B of alloys is brass and bronze. These copper alloys can corrode, especially in marine environments where salt is present. Number 4 of the most commonly affected materials is protective measures, includes. Number A of protective measures is coatings. Applying protective coatings like paint, galvanization, or anodizing can help prevent atmospheric corrosion. Number B of protective measures is alloying. Using corrosion-resistant alloys, such as stainless steel, can enhance durability. Number C of protective measures is environmental control. Reducing exposure to corrosive elements like moisture, pollutants, and salts can mitigate corrosion. Understanding the materials affected by atmospheric corrosion and implementing protective measures can significantly extend the lifespan of structures and components. Atmospheric corrosion critical factors based on API 571. Critical factors include the physical location, industrial, marine, rural, moisture, humidity, particularly designs that trap moisture or when present in a cooling tower mist, temperature, presence of salts, sulfur compounds and dirt. Marine environments can be very corrosive, 20 mili per year, as are industrial environments that contain acids or sulfur compounds that can form acids, 5 to 10 mili per year. Inland locations exposed to a moderate amount of precipitation or humidity are considered moderately corrosive environments, 1 to 3 mili per year. Dry rural environments usually have very low corrosion rates, less than 1 mili per year. Designs that trap water or moisture in crevices are more prone to attack. Corrosion rates increase with temperature up to about 250 degrees Fahrenheit, or 121 degrees Celsius. Above 250 degrees Fahrenheit, or 121 degrees Celsius, surfaces are usually too dry for corrosion to occur except under insulation. Chlorides, H2S, fly ash and other airborne contaminants from cooling tower drift, furnace stacks and other equipment accelerate corrosion. Bird turds can also cause accelerated corrosion and unsightly stains. Atmospheric corrosion is influenced by several critical factors that determine the rate and severity of the damage. Here are the key factors. Factor number 1 is moisture. Description of moisture. The presence of water in the form of fog, dew, precipitation, or high relative humidity is essential for atmospheric corrosion to occur. Moisture acts as an electrolyte, facilitating electrochemical reactions. Impact of the moisture to the atmospheric corrosion. In completely dry conditions, corrosion is minimal. However, in humid environments, corrosion rates can significantly increase. The critical factors number 2 is oxygen. Description of oxygen. Oxygen in the atmosphere reacts with metals, forming oxides. For example, iron reacts with oxygen to form iron oxide, rust. The impact of oxygen. Oxygen is a key reactant in the corrosion process, and its availability can accelerate the formation of corrosion products. Critical factors number 3 is pollutants. Description of pollutants. Industrial pollutants like sulfur dioxide, SO2, and chlorine can accelerate corrosion by forming acidic compounds when combined with moisture. Impact of pollutants. Pollutants can create aggressive environments that enhance the corrosion process, particularly in industrial areas. Critical factors number 4 is salts. Description of salts. Salts, especially those containing chloride ions, can form electrolytes that enhance electrochemical reactions leading to corrosion. The impact of salts. Coastal and marine environments with high salt concentrations can significantly increase corrosion rates. Critical factors number 5 is temperature. Description of temperature. Higher temperatures can increase the rate of corrosion by making electrolytes more reactive and accelerating chemical reactions. Impact of temperature. Temperature fluctuations can also lead to condensation, which provides moisture for corrosion. Critical factors number 6 is material properties. Description of material properties. The inherent properties of the material, such as its composition, microstructure, and surface condition, affect its susceptibility to corrosion. Impact of material properties. Materials with protective oxide layers or corrosion-resistant alloys can better withstand atmospheric corrosion. Critical factors number 7 is exposure time. Description of exposure time. The duration of exposure to corrosive elements plays a crucial role in the extent of damage. The impact of exposure time. Longer exposure times generally lead to more severe corrosion. Critical factors number 8 is environmental conditions. Description of environmental conditions. Factors such as air pressure, wind speed, and the presence of other atmospheric constituents can influence corrosion rates. Impact of environmental conditions. These conditions can affect the distribution and concentration of corrosive agents on material surfaces. Understanding these critical factors is essential for developing effective strategies to prevent and mitigate atmospheric corrosion damage. Atmospheric corrosion affected units or equipment based on API 571. Number A. Piping and equipment with operating temperatures sufficiently low to allow moisture to be present. Number B. A paint or coating system in poor condition. Number C. Equipment may be susceptible if cycled between ambient and higher or lower operating temperatures. Number D. Equipment shut down or idled for prolonged periods unless properly mothballed. Number E. Tanks and piping are particularly susceptible. Piping that rests on pipe supports is very prone to attack due to water entrapment between the pipe and the support. Number F. Orientation to the prevailing wind and rain can also be a factor. Number G. Piers and docks are very prone to attack. Number H. Bimetallic connections such as copper to aluminum electrical connections. Atmospheric corrosion can affect various units and equipment in different industries, particularly in environments where moisture, pollutants, and salts are present. Here are some of the most commonly affected units and equipment. Number 1 is storage tanks. Storage tanks description. External surfaces of storage tanks, especially those made of carbon steel, are prone to atmospheric corrosion. Storage tanks impact. Corrosion can lead to thinning of the tank walls, leaks, and potential structural failure. Number 2 is pipelines. Pipelines description. Above-ground pipelines, particularly those without protective coatings or with damaged coatings, are susceptible to atmospheric corrosion. Pipelines impact. Corrosion can cause leaks, ruptures, and significant maintenance costs. Number 3 of the most commonly affected units and equipment is structural steel. Structural steel description. Structural components such as beams, columns, and supports in industrial facilities are often exposed to the atmosphere. Structural steel impact. Corrosion can weaken the structural integrity, leading to potential safety hazards. Number 4 of the most commonly affected units and equipment is heat exchangers. Heat exchangers description. External surfaces of heat exchangers, especially those located outdoors or in corrosive environments, can suffer from atmospheric corrosion. Heat exchangers impact. Corrosion can reduce heat transfer efficiency and lead to equipment failure. Number 5 of the most commonly affected units and equipment is cooling towers. Cooling towers description. Components of cooling towers, including the framework and piping, are exposed to moist and often polluted air. Cooling towers impact. Corrosion can lead to structural damage and reduced cooling efficiency. Number 6 of the most commonly affected units and equipment is electrical equipment. Electrical equipment description. Outdoor electrical equipment such as transformers, switchgear, and junction boxes can be affected by atmospheric corrosion. Electrical equipment impact. Corrosion can cause electrical failures and increase the risk of short circuits. Number 7 of the most commonly affected units and equipment is insulated equipment. Insulated equipment description. Equipment with insulation, such as pipes and vessels, can experience corrosion under insulation, CUI, when moisture gets trapped. Insulated equipment impact. CUI can lead to severe localized corrosion, often going undetected until significant damage has occurred. Number 8 of the most commonly affected units and equipment is machinery and equipment. Machinery and equipment description. Outdoor machinery and equipment, including pumps, compressors, and conveyors, are exposed to atmospheric conditions. Machinery and equipment impact. corrosion can lead to mechanical failures and increased maintenance requirements. Understanding the affected units and equipment and implementing appropriate mitigation strategies can help maintain the integrity and longevity of industrial assets. Atmospheric corrosion appearance or morphology of damage based on API 571. Number A. The attack will be general or localized, depending upon whether or not the moisture is trapped. Number B. If there is no coating, corrosion or loss in thickness can be general. Number C. Localized coating failures will tend to promote corrosion. Number D. Metal loss may not be visually evident, although normally a distinctive iron oxide, red rust, scale forms as shown in Figure 4.72, atmospheric corrosion of an LPG line in close proximity to a cooling tower. The appearance or morphology of atmospheric corrosion damage can vary depending on the material and environmental conditions. Here are some common forms and their characteristics. Number 1 is uniform corrosion. Uniform corrosion description. This type of corrosion appears as a uniform layer of rust or oxide over the entire surface of the metal. Uniform corrosion appearance. The surface becomes dull, rough, and may have a frosted look. Over time, the metal may thin uniformly. Number 2 is pitting corrosion. Pitting corrosion description. Localized corrosion that results in small, often deep pits or holes in the metal. Pitting corrosion appearance. The surface shows scattered pits, which can be difficult to detect initially but can lead to significant damage over time. Number 3 is crevice corrosion. Crevice corrosion description occurs in confined spaces where stagnant solutions can accumulate, such as under gaskets, washers, or deposits. Crevice corrosion appearance. Corrosion is concentrated in crevices, leading to localized damage that can be more severe than the surrounding areas. Number 4 is galvanic corrosion. Galvanic corrosion description occurs when two dissimilar metals are in electrical contact in the presence of an electrolyte, causing accelerated corrosion of the more anodic metal. Galvanic corrosion appearance. Corrosion is often seen at the junction of the two metals, with one metal showing significant degradation. Number 5 is filiform corrosion. Filiform corrosion description, a type of corrosion that occurs under coatings, appearing as thread-like filaments. Filiform corrosion appearance. The surface shows fine, thread-like lines of corrosion under the paint or coating, often spreading from a point of damage. Number 6 is exfoliation corrosion. Exfoliation corrosion description, a severe form of intergranular corrosion that causes layers of the metal to peel away. Exfoliation corrosion appearance. The metal surface appears to be flaking or delaminating, often seen in high-strength aluminum alloys. Number 7 is rust staining. Rust staining description, commonly seen on iron and steel, where rust forms and can stain surrounding areas. Rust staining appearance. Red-brown rust stains that can spread to adjacent surfaces, often seen on buildings and infrastructure. Atmospheric corrosion visual identification. Uniform corrosion, general dulling and roughening of the surface. Pitting corrosion, small, deep pits scattered across the surface. Crevice corrosion, localized damage in confined spaces. Galvanic corrosion, corrosion at the junction of dissimilar metals. Filiform corrosion, thread-like lines under coatings. Exfoliation corrosion, flaking or peeling layers of metal. Rust staining, red-brown stains on and around corroded areas. Understanding the appearance and morphology of atmospheric corrosion can help in early detection and effective mitigation. Atmospheric corrosion prevention and mitigation based on API 571, surface preparation and proper coating application are critical for long-term protection in corrosive environments. Preventing and mitigating atmospheric corrosion is crucial for maintaining the integrity and longevity of materials and structures. Here are some effective strategies. Number 1 is protective coatings. Protective coatings description, applying protective coatings such as paint, powder coating, or galvanizing creates a barrier between the metal and the environment. Protective coatings impact. These coatings prevent moisture and oxygen from reaching the metal surface, significantly reducing corrosion rates. Number 2 is cathodic protection. Cathodic protection description. This method involves using sacrificial anodes or impressed current systems to protect metal surfaces. Cathodic protection impact. Cathodic protection redirects corrosive currents away from the metal, extending its lifespan. Number 3 is material selection. Material selection description. Choosing materials that are inherently resistant to corrosion, such as stainless steel, aluminum, or specially coated metals. Material selection impact. Corrosion-resistant materials can withstand harsh environmental conditions better, reducing the need for frequent maintenance. Number 4 is environmental control. Environmental control description. Reducing exposure to corrosive elements by controlling humidity, pollutants, and salts. Environmental control impact. Implementing proper drainage and ventilation systems can prevent water accumulation and minimize corrosion. Number 5 is regular maintenance and inspection. Regular maintenance and inspection description. Conducting routine inspections to detect early signs of corrosion and addressing them promptly. Regular maintenance and inspection impact. Early detection and repair can prevent minor issues from escalating into major problems, saving costs and extending the life of the equipment. Number 6 is use of inhibitors. Use of inhibitors description. Applying chemical inhibitors that slow down the corrosion process. Use of inhibitors impact. Inhibitors can be added to coatings or directly applied to metal surfaces to provide additional protection. Number 7 is design considerations. Design considerations description. Designing structures to minimize areas where water can collect and ensuring easy access for maintenance. Design considerations impact. Good design practices can reduce the likelihood of corrosion and make maintenance easier. Number 8 is monitoring and testing. Monitoring and testing description. Using sensors and other monitoring tools to continuously assess the condition of materials and detect corrosion. Monitoring and testing impact. Continuous monitoring allows for timely interventions and better management of corrosion risks. Implementing these strategies can significantly reduce the impact of atmospheric corrosion and help maintain the structural integrity of materials and equipment. Atmospheric corrosion inspection and monitoring based on API 571, VT and UT are techniques that can be used. Detecting atmospheric corrosion damage involves various inspection and monitoring methods to ensure early detection and effective maintenance. Here are some commonly used techniques. Technique number 1 is visual inspection. Visual inspection description. The simplest and most direct method, involving a thorough visual examination of surfaces for signs of corrosion such as rust, discoloration, or pitting. Visual inspection tools, magnifying glasses, borescopes, and drones for hard-to-reach areas. Visual inspection impact allows for the identification of obvious corrosion damage in areas needing further investigation. Techniques number 2 is ultrasonic testing, or UT. Ultrasonic testing description. Uses high-frequency sound waves to detect thickness loss and internal defects in materials. Ultrasonic testing tools, ultrasonic thickness gauges and flaw detectors. Ultrasonic testing impact, provides precise measurements of material thickness and can detect subsurface corrosion. Techniques number 3 is radiographic testing, or RT. Radiographic testing description. Uses X-rays or gamma rays to create images of the internal structure of materials, revealing hidden corrosion. Radiographic testing tools, X-ray and gamma ray equipment. Radiographic testing impact, effective for detecting internal corrosion and defects that are not visible on the surface. Techniques number 4 is electrochemical methods. Electrochemical methods description. Techniques such as electrochemical impedance spectroscopy, EIS, and linear polarization resistance, LPR, measure the electrochemical properties of materials to assess corrosion rates. Electrochemical methods tools, electrochemical cells and potentiostats. Electrochemical methods impact, provides detailed information on corrosion mechanisms and rates. Techniques number 5 is magnetic flux leakage, or MFL. Magnetic flux leakage description. detects corrosion and pitting in ferromagnetic materials by measuring changes in magnetic flux. Magnetic flux leakage tools, MFL scanners and sensors. Magnetic flux leakage impact, useful for inspecting pipelines, storage tanks, and other large structures. Techniques number 6 is acoustic emission testing, or AET. Acoustic emission testing description monitors the release of energy from a material under stress, which can indicate the presence of corrosion or cracking. Acoustic emission testing tools, acoustic emission sensors and data acquisition systems. Acoustic emission testing impact, effective for continuous monitoring and detecting active corrosion processes. Techniques number 7 is corrosion coupons and probes. Corrosion coupons and probes description, metal samples, coupons, or probes are exposed to the environment and periodically analyzed for weight loss or corrosion products. Corrosion coupons and probes tools, corrosion coupons, electrical resistance probes. Corrosion coupons and probes impact, provides direct measurement of corrosion rates over time. Techniques number 8 is non-destructive evaluation, or NDE. Non-destructive evaluation description, a broad category that includes methods like eddy current testing, thermography, and dye penetrant inspection. Non-destructive evaluation tools, eddy current probes, infrared cameras, dye penetrants. Non-destructive evaluation impact, allows for the detection of surface and subsurface defects without damaging the material. Techniques number 9 is remote monitoring systems. Remote monitoring systems description, use sensors and data acquisition systems to continuously monitor environmental conditions and corrosion rates. Remote monitoring systems tools, wireless sensors, data loggers, and cloud-based monitoring platforms. Remote monitoring systems impact, enables real-time monitoring and early detection of corrosion, facilitating proactive maintenance. Implementing these inspection and monitoring methods can help in the early detection and effective management of atmospheric corrosion, ensuring the longevity and safety of structures and equipment. Thank you.